time-dependent perturbation theory. Time-dependent perturbation theory, which in the first place just means that we make a series expansion again. So psi of t, we expand in a series of 0th order plus the 1st order correction and so forth. And the 0th order, that is this one. That's the solution to the unperturbed Hamiltonian, the field-free Hamiltonian, but it has to be time-dependent still. So we have to include the time dependence, which we normally always drop. And you will see a bit later today also why in the time-independent case, or in the case where there's no time dependence in the Hamiltonian, we can drop this term because it goes out. But if you want to have the full wave function, you have to have it. Now, we don't have infinite amount of time to do that, so I want to jump over the time-dependent perturbation theory part, derivation of how to get this first correction, and just write it up. I rather want to show you a derivation of some other things later on. So in this course, we're not going to look how to get this one. So I just write up what it ends up with. That is a slightly long expression. There are different ways you can do that. I'll show you one way, I can mention another one, but for what we're going to do today, this is a convenient way to write it up. So this is basically this factor, or is that factor. Then I get 1 over I h bar, and I get an integral from minus infinity to t. And that t, I mean that's time, and that is the t, I mean we are at some point in time, t, and that perturbation might have been acting already for some time. So what in principle I have to do, I have to sort of integrate from minus infinity from the sort of the start of time until the time I am at in the moment. And during that period, that perturbation might have perturbed my system. So I'm going to integrate at the end over a dummy integration variable, which we called t prime. So t prime is a time variable going from minus infinity to t. And then I get the same exponentially, almost the same exponential, but now obviously always with t prime. My perturbation, function of prime to all the times t prime up to the present time, which is t. T prime I h bar, and all that acting on the unperturbed time-independent state. So basically what that integral is that I have the perturbation acting on my unperturbed state from minus infinity to the time now. And it's a first order because it's the perturbation to the first power acting on my unperturbed state. And that's sort of accumulating how that state changes. Another thing you can see, this here you have your perturbation operator sandwiched between these kind of two exponentials here with e to the whatever operator that is, and here e to the minus that operator. That's very much like the couple cluster theory, where we also had the Hamiltonian and then the couple cluster operator, and we sandwich it off from the left with e to the minus that couple cluster operator. That is actually called the interaction picture representation of the perturbation. There are different formulations of quantum mechanics. There's a Schrödinger picture, there's a Heisenberg picture, and there's an intermediate one between them, which is called either the interaction picture or the Dirac picture. And if I would use that here, then I could write this just as the perturbation operator in that interaction picture. So that's a first order wave function. A second order wave function is very similar, just much longer, because then we have twice the operator, the perturbation operator, acting on this. An integral over, two integral over time with two perturbation operators acting on the unperturbed wave function. Now, up there I have the Schrödinger equation, the time-dependent Schrödinger equation. I have my Hamiltonian partitioned in the unperturbed and a perturbation, like we always do in perturbation theory. I make an expansion of my wave function in unperturbed and corrections of higher and higher order, and obviously I insert both that and this in my Schrödinger equation, and then I work on that. And doing that, for example, I got this first order correction. But there's one big difference to the perturbation theory we have looked at so far twice. One in general, and then Müller-Blechett perturbation theory. And actually also last time I've been there, we used perturbation theory, time-independent perturbation theory for looking at properties. But in all that cases we had the time-independent Schrödinger equation where we also had the energy in there. And then we also made an expansion of the energy and actually derived expression for properties as derivatives of that energy. We can't do that here. There is no energy. The time-dependent Schrödinger equation, there is no energy in there. So we can't derive properties as derivatives of an energy because there is no energy. Well, there are two solutions to that problem. How to define now time-dependent properties and use time-dependent perturbation theory to get expression for them. One is the one which I'm going to do now with you, which is not using the expression in terms of energy derivatives, but using the expression in terms of expectation values of operators. And I started originally out 2 weeks ago with an expression for the dipole moment being the expectation value of the dipole moment operator. That I still can do here. The other alternative is, which I'm not going to discuss in this course, but over the last 10-15 years got really popular, is that a lot of people, all the people who like to consider properties as derivatives of the energy, were really, really unhappy because there was no energy. So they just defined themselves something which looks like the energy, and in this time-independent case becomes the energy. It's called the quasi-energy. And then they can use all their tools and all the theory of defining properties as derivatives of energy to this quasi-energy. So there's an alternative way, and now it is quite popular, modern way of doing time-dependent perturbation theory on something which is called a quasi-energy. And the quasi-energy is basically the expectation value of h minus that time derivative. That is defined. That expectation value is then called the quasi-energy, and people work on that.